Good morning, everybody. Welcome to class this morning. I'm glad that you were able to find it. For those of you who are here with me live, thank you for joining me live. For those of you who are watching this later on in the recording, thank you for watching. I hope you find these live streams and these videos valuable to you. We're going to be covering a lot of the material in the class. In these live streams, we'll be doing some programming a little bit later on. In some of the future live streams, we'll be doing more in-depth programs, things of that nature, to try to get you accustomed to working in Java. And really, that's what Module 1 here is about. When I look at what we need to do to kind of get started in a semester, and I look at the types of students who are entering one of my classes, what I see is a wide range of students. I see students who have never programmed before, and they are just getting started and trying to try something new for the first time. And I see students who have, practiced some programming before, maybe done some programming and taken some programming classes before. And they're wanting to expand their knowledge a little bit with a little knowledge of Java. And so this class is a class that I try to make for all of these people, for people who have never programmed before, and for people who are, beginning programmers, maybe with a little bit of experience under their belt, just getting started on their journey to learning how to program or wanting to learn how to program in Java. And so when we approach Module 1, the thing that I can best think of for us to do is to just kind of get in a mindset of how we program and the things that we need to know to become a good programmer. Because it is a really different way of thinking when you approach programming and you approach something new like this. So having the options to kind of get started slow, kind of dip your toe into things before you really dive deep, I think that's pretty critical. And I guess for a moment I should speak about these live streams. I know they're probably a little different to you. You've probably not encountered a class that does their live interactive classes via YouTube like this. But it was like I mentioned in my announcement post in the course. My goal here is to have a platform that people are relatively familiar with. Like, I think pretty much everybody these days uses YouTube for something or another. Like, typically, if you're going to go learn something, one of the places where you start might be YouTube. So I think, having these live streams on this platform, a place where you're already probably going, is going to be a good idea. And also, unlike things like Zoom or Teams, you don't have to have any additional software to be able to watch this material. You can just click the link and start watching on YouTube. So I think that's beneficial. And also, if you're here with me live, which is not a requirement, but if you are here with me live, you can participate and engage in the chat, ask me questions, about the material, get some clarifications on things. So if you are able to attend live, then there is benefit for that to you. So now that we've kind of got the introduction down just a little bit, let's start talking about what we're going to do today and then parlay ourselves into the content. So what I would like for us to do is talk about the content here for a little bit. We'll just talk a little bit about thinking like a programmer. And then for the later part of our live stream this morning, what I'd like us to do is jump over to our online IDE just so I can show you a few things in it, and so that you know how to kind of navigate and access things. So what we're doing is we're starting out with thinking like a programmer. And I think when we're thinking like a programmer, one of the first things that we need to do is we need to kind of define some terms. So let's start out by defining some terms like, what is programming? When we think about programming, a program is kind of broad, right? And programming, being the creation of a program, allows us to do a lot of different things. And what we have here are we have some key functions of a program that, regardless of the programming language you're using, whether it's Java or Python or C++ or C Sharp or Go or Ruby or whatever of the myriad of programming languages out there you're working with, we're able to do these things with every single programming language. Now, when we're talking about a program specifically, we're talking about a sequence of instructions that specifies how to perform a computation. Well, what is an instruction? For our purposes, an instruction is just a line of code. It is a single statement. It is a single instruction that tells our computer to do something. And when we think about instructions in this sort of way, we can think about them like instructions that we get in a product. You know, like let's say for a minute, like, you go to IKEA, you get a new table. You bring that table home. You take that table out, and you have this instruction manual that goes with it. And each instruction in that instruction manual, they probably have them labeled, numbered, and in sequential order. So if you follow the steps, step by step by step by step, at the end, what starts out as just like several hunks of wood, at the end, you end up with a table. And that's essentially what we're doing here with our program. Like, each instruction is just a single line of code that does one particular thing. But when our interpreter executes our instructions, one after another, after another, after another, what you end up with is your finished product, your program. And the program being the performance of some kind of computation. So what is a computation? Well, when we're talking about computations in this sort of way, we could be talking about them in a way that you're probably familiar with, like math, solving equations, doing math problems, figuring things out. So that's one of the types of computations that we might be solving, and the other type being symbolic sort of computations, things that utilize strings and words, characters. Maybe we're going to go through a document and take all of a particular type of word. We're going to strip that out of there. Or we're going to do some string manipulation and replace certain characters in a word. That's not math. But under our understanding of programming, that's still the performance of a computation. Because really, when we break everything down to machine language, the binary that our computers talk in as their native tongue, what you end up with is, a series of ones and zeros. And we can kind of look at that in terms of, on and off, true and false. With our computer, it's either, we're sending an electrical signal or we're not. And these are the things that are kind of crucial to understanding, but it forms the foundation of this 1 and 0, and everything is communicated with ones and zeros, which are numbers. So even things that are symbolic sort of computations that use words and letters and Boolean operators and all of these other sorts of types of data, when they're broken down to their bare bones in computer language, they're ones and zeros, they're math. So we can think of everything in that sort of way. But every program has the ability to, or every programming language has the ability to do these particular things that we have here. And how you do them is going to be different, right? Like if I write an input statement in Java, it's going to look very different from an input statement in Python. How you do them is going to be different. We call that how you do them, how you write the specific lines of code. We call that syntax. But the fact that you can do them and implement them into programs is universal. And so when we get into these different when we get into these different elements of our programs and we start to figure out how to take all these different little puzzle pieces and put them together to look like the picture that's on the box, right? To be that final computation that we want it to be, when we start to take these different instructions and arrange them in the right order to do what we want our program to do, we call that logic. So there are two sides of any program. We have the syntax and we have the logic. And the syntax, really, for all intents and purposes, the syntax is easy, right? When we are thinking about syntax, the syntax is just the specific way that something's written, where we put our semicolons, where we put our parentheses, where we put commas or curly braces or what have you. That stuff can be looked up and gotten from a book. I'm not going to expect you to memorize every single little bit of syntax, nor really should you have to. You know, when you get into the real world, if you get a programming job out in the real world, you might encounter a problem that you've never seen before. You know, programming languages are huge, and the things that you can do with them are vast. So it's highly likely that you're going to encounter something brand new. So being able to kind of look up the answer and figure out what you need to do in a certain situation is crucial. It's important. But you can simply just look it up. What's a little harder to look up is the logic part. That's something that you have to kind of learn and gain and understand. You know, because we can put these in any kind of order. It's just depending on how our brain understands that we need to put these things in order so our interpreter can read them, execute the instructions in the right order, and give us the output that we intend. So this isn't something that can come from a book. This is something that we have to think about and reason through and work through, which makes it much harder. And another thing that makes programming much harder that I'll go ahead and throw out right now is the fact that there's no one solution to a problem. Again, programming languages are vast. They're huge. There's all sorts of stuff that's included in a programming language. And oftentimes you can go through and you can write 6 different programs, 7 different programs, 20 different programs that do the exact same thing but look completely different. And programs are going to vary based on people's logic decisions and how they approach problems. And that's okay. At the end of the day, what we're looking for is, does the program work? Is it relatively efficient? If the answer to both of those questions are yes, then your program is correct. And this is something that's often a challenge for a lot of students because they come into a class, and most of the time when you go into a class, like, you expect there to be a right answer and a wrong answer. And, you know, like if you are in a math class or you have these problems and you're working through these problems, each of those problems has an answer. And you can get that answer right or wrong. If you're, in another type of technology class, like a networking class, there's generally one way that you have a process to go through and set up a router, to query an access table, to subnet. There's typically one general process that allows us to do this. So there's a right answer and a wrong answer. But now I'm facing you here at the beginning of this course where I'm telling you that essentially the right answer is something that works, anything that works, and the wrong answer is when the program doesn't work. So that leaves a lot of gray area in the middle there, and that does make things difficult. But as we approach these problems, I hope you'll find that as you get more comfortable with programming, get more comfortable with the different pieces of the pie, as it were, that your problem-solving path is going to become more and more efficient and strong and solid as we progress throughout the semester. So that's programming in a nutshell. That was one slide. We need to move through these probably just a little bit quicker. I normally don't like going too long for these live streams. I like them to be relatively, short, 30 to 45 minutes at the longest. And I still have a lot of things to talk about today. But that's programming in a nutshell. Let's talk about computer science. So in talking about computer science, what I'm going to do here is I'm going to take some terms that sound like big, scary terms, and I'm going to break them down to make them more accessible. For example, computer science is the science of algorithms. When we think about computer science, oftentimes, we think about a lot of like highly technical, highly advanced concepts. But when we break computer science down to its essence, it's really just the science of algorithms. But then we have the word algorithm, and algorithm's a big, heavy word. But what really is an algorithm? Well, if we take algorithm and we break that term down, an algorithm is simply a sequence of steps that specifies how we solve a problem. So if I'm going to algorithmically determine something, I'm just going to have a programmatic sequence of instructions that at the end of that sequence, I'm going to have an answer to my question. Now, one of the things that we want to remember, though, is that designing algorithms and writing code, it's difficult and it's error prone, especially when you're just getting started with it. It's going to be complicated. I'm going to tell you right now, it's going to be complicated. There are going to be times when you're like, oh man, and you're going to get real frustrated. When you get into the trenches and start working on some of these bigger problems that we'll be working on down the road, huge frustration, huge emotion. Which is something that comes through that you might not expect. This big wave of emotion in programming being emotional. Because after you've, banged your head into the wall for hours trying to figure out how to do the right thing to make this program work properly, there are feelings that can kind of take over. And one of the big things to remember as we kind of approach all this is that it's new. It's going to be challenging. Be prepared for that now. Persistence is just as important a concept in programming. Being able to not give up until you figure out a solution for your problem, seeing it through to the end, is just as important a skill to have as a programmer as knowing syntax, learning logic, that sort of thing. Just being able to take these errors in your code and work with them until you can figure out a way to fix them. Now, we call these, for historical reasons, we call these errors bugs. And the process of tracking them down and correcting them is called debugging. Now, I think my next slide actually shows you the very first bug this is where the idea of the bug came from. And it's actually taped here to these notes. It was on a U.S. naval vessel back when we had more mechanical parts in computers. You can see that under the tape here is a moth, and this moth actually flew into the machinations of the computer and got caught, which prevented things to happen within that computer. So the first actual computer bug was an actual bug. In specific, it was a moth. And this is a picture of it. So, you know, it kind of, the idea of calling an error in a piece of software a bug actually came from this, which is, you know, it's interesting. It's a cute little story. You know, just kind of a little anecdote as a side thing that explains where that name came from. But when we're thinking about it, algorithms, one of the things that I like to bring up when I'm talking about algorithms is the idea of algorithm bias. And so this is just something that is important to remember as we approach the problems that we are solving. Because the problems that we're solving are defined by the people that are solving them. So you and I, as the programmer, when we're understanding a problem, we're the ones that are defining that problem, and we're the ones that are stating what that problem is. So thereby, since we're defining that problem and we're writing the program, we're also writing the means to which we think we should solve that problem. So oftentimes we think about computers and software kind of being robotic and you know, without any kind of biases or just, you know, just kind of a, you know, it's a computer, right? Like it doesn't think, it doesn't have an understanding of the world. But when we think about the problem that we're solving and how we solve that problem, since the programmer themselves are the ones who are solving the problem, what's happening then is that we are kind of influencing how the software solves problems implicitly or sometimes even explicitly based on our own values, based on things that we believe to be true. So it's important as we go into this idea of creating algorithms, and we're not going to create anything that's going to cause any social issues in this course. You know, nothing that we make here is going to, you know, be on the precipice for society's downfall. But the algorithms and the programming that go into software or go into a website or go into whatever, you know, even though we think about them as being, you know, robotic, without feeling, without emotion, without bias, these programs were made by people. And while computers themselves don't have emotions or feelings or bias, people do. And we can implicitly or explicitly include those biases in the software. And you know, one of the places where that's really big right now is the idea of AI in autonomous vehicles. You know, you might have heard some of the discussion about when the vehicle makes the decision to brake versus veer versus hit whatever's in the road. You know, what is the value placed on whatever is in the road that might present an obstacle to that car, and how does it weigh the value of that versus the value of protecting the driver? And so you hear, it's like, well, if it's an object, if it's an animal, if it's a human, and then how do we recognize humans with machine vision? The decisions on what happens here, that's made by people. So while we're talking about algorithms, we may as well go ahead and bring that up, that we have to have this understanding of a more global society, of a larger realm through which we solve our problems as we're approaching algorithm design. Now, our software is so influenced, right? Because really, we like to think of our computers being smart. Like, oh, we can get on our computer and our computer can do whatever we want it to do. But really, our computers are pretty dumb. Our computers are dumb. And this is another big important thing to understand before we get started programming, is just how dumb our computers are. And how important specificity is when we are solving problems and writing code. And in terms of this, I always bring up an ASCII table. We have our ASCII table here, and inside of our ASCII table, that's how our computers understand what a letter is. Right? So for example, you and I, we're smart. We know what we're doing. We know the score. If we see this letter here and this letter here, we can easily identify these letters. We can look at that and we can say, oh, those are T's. The one on the left, that's an uppercase T. The one on the right, that's a lowercase t. However, I know that they're both T's. If I look at this word, and this word, I can say, well, oh, those are both the word tree. That's tree. That's tree with an uppercase T. That's tree with a lowercase tree. They're both trees. Our computer doesn't see it like that. Our computer sees it through an ASCII table. So when it sees that uppercase T, what it sees is the value communicated to it in machine language or in computer code. That's the number 84. And this lowercase t, well, it's not a T. That's 116. So when our computer sees these things, they see two totally different things. And as a result, they see these two different words. They see these two words. Those are totally different words. That's capital T, uppercase T tree, not the same word as lowercase t tree. Because of the way that our computer understands letters. And we actually see this, we can break this down even further in binary, because we take each character and we can break it down to a binary octet. And so if we break down our uppercase T to a binary octet, what we end up with is going to be 0, 1, 0, 1, 0, 1, 0, 0. So that's going to be the binary octet for our uppercase T number 84 on our ASCII table. So when we put in the uppercase T, this is what our computer gets. Conversely, when we look at the lowercase t, well, that binary is going to be 0, 1, 1, 1, 0, 0, 1, 0. That's our binary octet for that. So that's what our computer sees when it sees that lowercase t. So two totally different things. So this is to tell you that whenever we get into our later programming and we start talking about variables and we start talking about different lines of code, capital S system and lowercase s system are two totally different things. Two totally different words. So if you're referencing the system class inside of one of your Java methods and you use a lowercase s in system on accident, it's not going to work. It's going to throw an error message because it's looking for the uppercase s system for the system class library. So it's important to have an understanding of that now as we approach these concepts so you don't make these little silly mistakes later. And this is something that's always challenging, right? Because again, we're smart. I look at those two words, I read system both times. Our computer looks at those two words. Those are two completely different words. And that's a big thing for us to understand at this point. So Java is what we call a high-level language. Just real quickly, trying to fly right through some stuff. Java is what we call a high-level language. Essentially, we can think of high-level languages and low-level languages. High-level languages are closer to natural language. And it's kind of a spectrum. When you get into high-level languages like Python is more close to a natural language than I would say Java is. But they're still both considered to be high-level languages. And when we say natural language, what we're talking about there is like a language that people speak in, like English. So I can read high-level programming language statements as English sentences. If X is greater than 7, then blah. Conversely, low-level programming languages are closer to machine language, closer to that binary. So when you're looking at that, you're looking at things like assembly or things that are kind of written at the microcomputer level. So high-level languages take less time to write, they're shorter, they're easier to read, and they're more likely to be correct. Another big thing about high-level languages is that they're portable. So with some addition of maybe some software on a computer, I can take a Java program from one computer and run it on another computer. I can take a Java program from one operating system on one computer and run it on a completely different operating system on another computer. That's important things to know about high-level languages. And then finally, let's talk for a minute about interpreters and compilers, because these are the things that read and run our code. And in our online IDE REPL, what we're using there is essentially an interpreter. It's going to read the high-level program, and it's going to execute what it says. So it's going to do what that program says. That's what an interpreter does. And so when we're working in our online IDE REPL, or really any IDE for that matter, and we're just running code as a test out of our IDE, we're utilizing our interpreter to read that code and execute it in the console or execute it wherever we have the code running. The compiler, conversely, reads the entire program and translates it completely. Essentially, it's going to make a new file most of the time before the program starts running. So in this case, the code that you write is called the source code, and then the compiler is going to take that source code and it's going to translate the entire thing and turn it into something that we call the object code or the executable. And you might have seen like an exe file, or in Java they'd be jar files. That would be your native executable. So this is the result of compilation or compiling. With our interpreter, we can take our .java file and just run it directly in our IDE and see the results. With a compiler, it's taking that original code that you write, converting it into something new that's more closer to machine language, and making it a different type of file that would be an executable, like a .exe or a .jar, J-A-R. And we can see kind of a flow of execution of the way these things look. In our graphic here on top, we have our interpreter. On the bottom, we have our compiled code. And so on the top, you see we just have source code, runs it through the interpreter, gives us the output. On the bottom, you see we start with a hello.java file, we compile it, and then we get bytecode out of it, which is going to be hello.class, or it's going to be hello.jar, or it could even be hello.exe, depending on the methods that you use for compilation. And then from there, that's an executable file that the user can click on, that once they click on it, will automatically run the code through an interpreter and give you the output. So that's the difference here. So that's essentially all the content that I want to talk about. But before we depart, I want to head over to REPL. And I want to show you some stuff on there just so we can make sure that we have an understanding of how this works before I turn you loose and let you finish up your assignments for this module and the remainder of the modules that we'll be working in. So once you log into REPL, you'll see a screen that looks something like this. Right? My screen's going to look a little bit different because I have more recent programs. You probably have nothing there if you're just now opening up your REPL account. You might have some stuff. You might have one that you had before, or you'll have a few programs in there. I have some quick languages here that I can access. I can create something new from here. I can create something in Python quickly, something in C# quickly, something in the HTML, CSS, JavaScript stack quickly. Or you can create something new. So we're going to come back to this page in just a moment because I want to talk about our team. But before we do that, I want to show you how you're going to complete your labs. So what we're going to talk about now is labs. Then we're going to circle back to talk about our team, which is going to be your small assignments. So when you're creating your lab, those labs are programs that you create from the base, from a scratch program. So what I'm going to want to do here, when I'm approaching one of those problems, I can either click this plus sign here or click this new REPL here. They're both going to give me the exact same menu. It's going to give me this place where I can select a language and name my REPL. So in selecting my language, you can see here that there are all sorts of languages that are here in Python, or in REPL, rather. And when we type in, and before I get too far, you know, if you want to practice in some of these other languages and tinker with some of these other languages, you can try them out. But ideally what you'll want to do here is you want to type in the word Java, and you'll see everything related to Java come up. Regular Java, right there at the top, that's the one that we're going to be using for 95% of our projects. When we get toward the end of the course, we'll need this one here, Java Swing. That's the one that's going to help us write our GUIs. But until we get to that last module where we're writing GUIs, we're going to stick with regular old Java. So we're going to select Java, and we're going to give it a name. So I'll have to name it something a little weird because I have tons of these now, but we'll call it Spring21, my first program. And for you doing this, like, you could probably just name it the name of the assignment, and that would probably be easy enough here. For the free accounts, which you all would have, you can only select public. They'll only be public REPLs. I have a paid account, so I could set mine to private if I wanted to. But public is fine. In fact, we'll need public because I'll need to be able to see them to grade them. So I'm going to just click Create REPL here, and it's going to give me a Java REPL here. And it's already populated a main.java for me. And it's already made a main class for me. And so one of the things to note as we're kind of getting started here is that this class name, in this instance, it's class main. Right? Let me zoom in so you can see that just a little bit better. This class name here, the class of your file, is the same name as your file name. And the interpreter actually looks for that. So if you have a different name between here and here, it's going to freak out. Like, I can even show you that. Like, if I change that to class prog main and run it, it's going to throw a fit. Could not find or load class main because it's looking for the main class inside of the main file. Now, one of the things that you'll also notice here is that REPL is kind enough to give us our main method, our main function inside of here too. Now, one of the differences here is this main function is in every Java file. The main function is the function in which our code executes. So this name main here is unrelated to this name main here. So it's a little confusing in terms of let me delete this compiled file here. It's a little confusing. Because they are the same name, but this name main here has nothing to do with this name main here. We have to have a main function or a main method like this to execute all of our code in Java if we're going to be executing code. And it actually gives us a hello world by default, this system.out.println. So when we run this, we click this run button here at the top, it'll compile the code and it'll run it. And we get our output, hello world. And we get a main.class file here. That's the compiled version of the code. So our REPL is actually kind enough to give us the hello world. System.out.println and then parentheses, and you put the string in quotes, hello world. And so hello world is typically the first assignment that you do in a lot of programming classes. It's, kind of your first foray into programming in that language. And you might be wondering, well, like, why did you give us that as the assignment if it gives us some of the code already? And this assignment isn't supposed to be difficult. This assignment isn't supposed to be hard. This assignment is supposed to be primarily about just you getting into the environment and just starting to do something. Playing with some code, executing some code, writing some lines of code, clicking the run button and seeing the output over here. This one's not supposed to be a challenge. It's not supposed to be something to try to stump you. That's for later. This one is to just get you comfortable with coding in an integrated development environment and actually starting to write lines of code. So now from here, when you get done, all you have to do to submit it to me, this URL up here, it's unique. And remember, it's public. So you can take that URL, you can copy that, and then when you get into that assignment in Blackboard, you just click on the assignment, scroll down to where you can submit it, click the Write Submission button, and paste that link right in there, and I can get it. I can open it on my end. I can see all the code you've done. I can run the code, and life is good. So it really utilizing this online IDE makes things easier for both you, just because of how friendly this is, and me, because it makes it a lot easier for me to grade. Now, when you're ready to go back home, you can click on the icon here at the top to go home. And we'll just briefly jump into the teams here. And we have a team. Looks like everybody's joined it. So we can see everybody in here. Looks like everybody's already joined the team. That looks pretty good. And we've got these team projects. And I can go through here and I can see all of the team projects. And I can view your submissions. So it looks like most of you have already figured out the environment and gotten going in it. And that's great. But all you have to do is you're just going to come to this point, click on teams in your sidebar, click on your team. It's not 2020 SP. I don't know why it put that there. I think probably because I used the same assignments this semester that I did last spring. So maybe I forgot to change something, but it's all right. It's current. It's fine. We just click the assignment. You complete the instructions, which you will find actually, I think I have to look at it from a student view. Oh, the instructions are in the readme.md file. That's right. The instructions are in the readme file. I'm sorry. They just right before the semester started changed from an old way of doing this, which was REPL for Education, into this new Teams way. So I'm still getting used to it myself. So it looks like a lot of you got used to it a little quicker than I did. But your instructions are in this readme.markdown file. Gives you a markdown file. This is where your instructions are. This is where you read what to do. And so it tells you here just to enter the code in the main.java file that will print out the text below exactly. I'm on my way to learning Java. And then you have this bit of code here where you can enter the code that you need to right here. And then once you do that, you click on this check mark here for tests and run the tests. And it'll check the tests for you and make sure everything works. If it passes the tests, you're good to go. If it fails the tests, you need some more work to try out. But the difference between these little small assignments and the bigger labs that we do, especially in later modules, is that these little small assignments just focus on like one part of the syntax or one little piece of something. Like it'll be like, oh, write an array that has this in it. Whereas the labs, especially later on, will be more of a snowball type of lab. And as we progress, we learn more and more, and our labs get bigger and bigger and more complicated. Right, so that's what we're looking at there. So that's just something to remember as you're going through. Then all you do back into Blackboard, you just give me a heads up in that assignment, letting me know that you've completed them. So I can go back to our Teams page and check out your submissions. And we've got these smaller assignments all the way through to Module 8. So after Module 8, there's no more of these, but it's just a good thing to get us started. So I think that will, I think that'll help you out and get you there along the way. So that's all that I have for you for today for this live stream. It's a good first live stream. It's a long first live stream. I don't normally like to go this long. I normally like to have them a bit shorter, but it is what it is. I'll hang out in the chat for a minute just in case anybody who's here watching live with me has any questions. If you're watching this later and you have some questions, send me an email. I'll answer them to the best of my ability. Again, this is the first time we're using this team setup. They just swapped to this like right before the semester started. So I'm kind of learning this setup a little bit too, along with you guys. So hopefully it'll work just fine. But that's all that I have for you for today. Thank you for watching. We'll see you next time.